Welcome to the lecture number 12. So in this lecture, we will continue the concept of variational principle to find out the shortest time or the shortest path to deal the practical problems. Okay, what we have seen yesterday is the Bernoulli's challenge called Barchistochrone problem, where the shape of the stone's trajectory or the roller coaster track, we raise the question. So today we can see that how the shortest possible timing that defines that path in such a way that they are not typically straight lines. And with this idea of introducing the element ds and bringing a functional form f of y prime x that we have discussed already, and then we simply solve a problem which giving a simple idea of how the function or the integral should be evaluated to give the value. Now we will discuss more about the variational principle. Let's get into that. Now, if you are given a choice, how would you justify the path the system takes during its action between a point A and B? So, if your exact integration path is not known, then you have options to imagine n number of possible paths between 2 points. That's what we said. For example, if we consider this plane, and 2 points on it, and if you want to reach the points, I can take the option 1 as a going with just a straight line, or I can take a some functional form of curve, or I can take the other functional form of curve, or the any options. Now the question comes to is that out of all these possible paths, in which path the integral would be stationary, or which path that would be stationary? So in order to justify that, you need to obtain a condition for this integral to be stationary, where the variable is the integration path. Now, how do we proceed? Let us look at it. Let's pose a question 1. The shortest distance between the 2 points on a plane without any constraint is a straight line. For example, that you see here on the right side, would it be like this? Or would it be any functional form? Option. So you have multiple ways of reaching between the points. So we have to prove it, and then we are going to do it with this variational principle. Similarly, if I take a sphere, which you see here, this is your sphere that you see, the shortest path between 2 points on the surface. You remember the sphere as an orange root. Now I'm just taking 2 points on a surface and trying to connect them. And these 2 points, the path that passing through would be always lying along the great circle, which I will explain. Great circle is nothing but a plane. If you cut the orange in a half a way, so that the surface you see is the projection of the surface is a circle, and that has to pass through the origin. That is what typically said to be great circle. We will look into that's what you see here. So if I cut this orange as half a way, that the surface you see is that projection of the surface can be represented in a circle which is passing through the origin as a center is the great circle. I'll explain it with the more explanation in the next class, that is on Saturday. Just wait for it. Now to answer these questions, you need a necessary condition. That the integral I, which is represented from x1 to x2 of the function f, which has a variable y prime x and dx, is stationary. The definition, when we say extremum, it can have either maximum or minimum. Okay, now how do we find this extremum of a function? That always comes. You have done it nicely in a simplest way, but let us rewind it how to do it. So let's consider a plane and a function passing through like this, that a path like this. Now if I want to find a minimum in this functional path, then I have to find for every x what is the function of x, which can be represented as a y equal to f of x. For example, if I take a point x here, for which I have a function which is y equal to f of x. In order to find the minimum, or in order to locate this minimum, we need to vary this x in a small element with the delta x and so on, moving all the way towards the right side. I can go up to a point which I like to be. So now if I increase this x from small, again a small value delta x here, so I can suppose I move to this point. So this is my first delta x, and then you will be obviously seeing the delta y corresponding changes. So if you keep on doing so, when I come to a point somewhere here, my delta y for a small delta x can be 10 to 0, such that the delta f that you see here, which is nothing but f of x plus delta x minus f of x. So if I vary a small delta x here at this point to this for a given x, then my delta y does not change, or delta f does not change for that small delta x. But if I further move from here to the next point here, if I am moving from this position x, if I move from this position of x to somewhere here as a delta x, then I have corresponding delta y change which may not be minimal. So in this curve, I am going to get a point where my delta f is also going towards 0 for small change in delta x. So what you have, if I take this as a point x naught, we can say that the function is stationary at x naught, because for a small step of delta x at x naught, the value of the function does not change. That means the delta f is going to be 0 for at x naught for a small change of delta x tends to 0. So this is the way of finding the extremum of a function. I'm sure you don't have any doubt on this. Now if this is correct, let us move on how to find a stationary condition of a function, or the stationary condition of a integral. Now if a stationary function condition of an integral, you can establish it by taking some steps to get the stationary condition of the function and making certain procedures. And that procedure is not very difficult. Let us consider the same curve, and the procedure number 1 says, suppose x is the point for which f of x is stationary. So in this curve, the x is your point here for which your function f of x is going to be stationary, because I know this is your x naught. If you consider it, if you add any delta x here, the delta f change for this small delta f is also nearly 0. So therefore, if you consider a path y equal to y of x, that also to be determined, for which the integration would be stationary, because there is no change in the delta f for it. That is what the meaning is. Now, the second step is that if we keep on adding all possible points by taking delta x to a given point, which differ from stationary point, suppose I move this side or move this side by a small amount of delta x of the way we consider this side also, if I consider a delta x increases slowly, then what would be analogy is that I have a function y of x at this point, which will also be varying with the small amount of delta y of x to represent all the possible paths between the points x1 and x2. So your value of delta y for each delta x is also going to be, so the value of y will be increased by delta y from the original value this way. So that's what we are saying, that it will be differed by value of delta y of x. Now we can consider that the variation of f of x such that if it is negligibly small near the stationary point, which gives the final condition that the change in the y to the x is 0, which means the variation of the integral value, because if that is the truth, then the delta I or the integral path which change from y plus delta y to the actual value y will also be small in the nearby path. That means the delta y is tending to 0. Okay, these are like steps that you consider, but how can we visualize it? Let us take a smart choice of the varied path to understand it more clearly. So let's say this is your actual path for which the integration I is stationary. Okay. Now we are going to choose a path, another path which is close to this path or any other variable paths, different paths, which I believe that that is my correct path, how they should be representing it. So let us choose a path which is actually y of x, which is given here, and then you add delta y to that, such that it can represent any possible path between x1 and x2 for different delta y. Now, if I take this function and if I just simply add, say, 5 with that, what will happen? You will be shifting all the points. If you add 5 here, let's say it will come here, assuming, and then I can draw this curve like exactly going to this way. So my B also will be shifted to plus 5. Everywhere my curve will be shifted by 5 units. In such case, you are not starting from A and ending to B. You are somewhere starting from C and ending to D. So you are completely taking a new path, which isn't correct. So we'll have to put a proper mathematical condition such that I can mathematically form this delta y such that when a delta y is added to this y of x, can represent all paths but must be having variations at, it should not have any variation at A and B. What is that meaning? Still not clear, right? So, and similarly, the second point says the delta y goes to 0 in the limiting case when the varied paths are close to y of x. Now, how do we put it? Because if I add any value delta y, my whole path is shifting. But then we are saying that no, it has to start from A and B. So we have to introduce some choice of delta y which carries in this functional form. For example, y of y equal to y of x plus delta y to add another path between A and B that you see as a pink color curve here has to have the delta y such that you see it is starting from A only, ending at B, but it is ordered with some delta y. So how do you represent a curve? So you have to choose the choice as the delta y with the two parameter, one is psi, other one is eta. Something very tricky, that's different. Now the eta has a special property that it is an arbitrary function of x. Remember, it can be any arbitrary function of x, but the condition is that the eta at x1 and the eta at x2 should be 0. So that even if I say like y, suppose if I take y1, if this is a y1 and this is y2. So if I do y2 equal to y1 plus eta psi, then what happens? When at x1 and x2 when this is 0, so this function will be turning out to be 0, giving my y1 only. So I will stand at this point and at this point without any condition. So therefore, the condition number 1 balances with such constraint imposed on it. Similarly, the psi is another parameter which I can vary from small value to large value to produce all possible curves of my paths that I can consider. But if we have to take it, the delta y goes to 0 means then you have to eventually psi tends to 0 to satisfy the condition number 2 here. Okay, now we got some mathematical functional form. Now we can introduce it to form a various curve so that you can understand very clearly. So we are taking a curve, a standard curve, which is an actual path y equal to y of x, which you have stationary. If I want to consider any other possible paths by relating to this, so let us put an eta of x, which has 0 at x1 and x2, otherwise it is non-zero. And now if I add this one with by multiplying some value psi, then I am going to get a new curve. So let us take the pink curve that is coming up is as another curve where the original path is ordered with delta y, where my psi is a small value and eta of x considered from here. I hope now you catch what would be the nearest path. Now I can take with the large value of psi, say something like 0.9 and then eta of x. Now I am deviating away from the original path. So by this way, you can consider as many as possible paths between the point A and B. Now I can take eta of x in different functional form here and construct the same way between the actual path to the variety of possible paths between the point A and B by varying the psi parameters and also the arbitrary function of eta of x. But then we can play with the mathematics just to produce the number of paths, but then you have to bring a statement or a condition to say that the path that we choose or the system chooses is the minimum path or the stationary condition it gives. How do we prove it? So, my idea is to bring that stationary condition. Suppose you have the variation of integral along a path that nearby to the stationary path is negligibly small. We can say that statement in this way. In the sense, if I have a original integral path and I take another path which is ordered with these small psi values, and the difference between these two, that is given as a delta of I of psi, should tend to 0 when my psi is approaching to 0, then I will always reach the stationary path which is my system going to exhibit it. So in such case, We know how to represent the integral path, which is the path between point x1 to x2 with the functional form of f y prime x dx, which is for the stationary path y equal to y of x. Now, if I consider another closest path, which is I of e here, psi here, then this psi will going to add a delta y in y and delta y prime in y prime, such that I am going to get a new function which is not only x, it will also have the y psi dependence also. So this is another path which is given by the form of y x psi is equal to y of x plus delta y, and this is delta y is given in the form of psi eta of x. Now what we are going to say is that this is equivalently, if I take a derivative of I with respect to psi, for the psi tending to 0, it should give the value 0 if the path that I am taking is going to be the stationary one. So the condition that we are imposing for the stationary path is di of psi by d psi for the psi tending to 0 is 0. Now in such case, let us take a derivative. Now if I go into derivative this function and we know this function, so now we are going to take derivative of this function using psi. And you know the function y is also is a psi dependent. So we are going to imply a partial derivative. So how do you put it? So we can take it x1 to x2. The first part is partial derivative of f with respect to y and the partial derivative of y with respect to psi. Similarly for y prime, you have partial derivative of f with respect to y prime and the partial derivative of y prime with the psi. Because the x is independent of psi, it does not depend on psi, therefore the derivative of x with the psi is simply 0, it would not be there. Now what is the value of the partial derivative of y with respect to psi? Because you know what is the y, it is the original, the stationary path plus psi eta. If I take a derivative of this y with respect to psi, it is only, so this will be derivative of y with respect to psi will be simply eta. Similarly, for the function y prime, it will be eta prime, right? So now we can substitute those values here. So we are going to get the partial derivative. So eta is placed here and this is eta prime comes. So we have now a function which can be rewritten using this functional form. Suppose if I take a d by dx of a and b, we can write it nicely that a of db by dx plus b dA by dx. This you know, so that is what it is written here. And now this function that you see here is existing here. So this can be replaced if I move this to minus this way. So we are going to replace this term with these two terms in the steps. So that would be coming out to be like this. So you have this term coming here minus this term is placed. Now, if you see this here, the midterm here, this is integral of differentiation, which is nothing but you can simply take out this term outside, right? Integral of differentiation would not affect the function. So, therefore, we can rewrite this midterm as partial derivative of f with the y prime eta x1, x2. Now, what would be the value of eta at x1 and the x2 point? It has to be 0 so that my path starts from A and reaches B. So, the condition of eta x1 and eta x2 is simply 0. So, therefore, this term can be made it to be 0. And since this also has eta dx, this also has eta dx, take it away commonly outside, then you can rewrite this function such that we have minus integral x1 to x2 with the derivative of d by dx of partial derivative f with the y prime minus partial derivative f with the y eta dx turns out to be 0. And you know that for every possible choice of eta, any arbitrary function which you cannot set to be 0, so the term inside this parenthesis should go to 0. And this is the condition that for the integral path I given in this functional form to be stated as a stationary, and this condition is called as a Euler-Lagrange equation. See, we are again coming back beautifully to the Lagrange part, similar to Lagrangian formalism. Right? Now let's compare between these two statements. Like if I have a function f given as f y prime x, then my Euler-Lagrange equation turns out to be d by dx of the partial derivative of f with the y prime minus the partial derivative of f with the y is 0. Because there is a 0, you can switch this term and therefore sign is not going to affect it. So I can write a minus b is 0 or b minus a is 0. Both is going to give the similar way of it. Now in the similar line, if we consider this Lagrangian formalism where you have L generalized coordinate, generalized velocity and time, you are writing d by dt of partial derivative of L with the generalized velocity minus the partial derivative of L with the generalized coordinate is 0, which can be also written by switching over. So if you see this simultaneously, remember the functional form, the f and L, they are of similar nature. Then this is the condition that is going to tell the equation of motion that comes out of this equation, this Lagrange's equation will be the path which is stationary. Is that true? How do I believe it? Sorry, sir, I still don't get it. Okay, mathematically we shown. Is that true? That is going to give. Okay, let's check with the simple examples of kinematics. If I say a particle existing in a potential, what it would be least action? So when you say particle, let's say simply one dimensional and the potential has a also position dependent. So we have T and you have U. So you can construct the Lagrangian. So Lagrangian says that kinetic energy minus potential energy. And this is a time dependent part, therefore we need to use this equation. So if I use this equation, the partial derivative of L with respect to x dot would be mx dot, and this is x dependent, so the partial derivative of L with respect to x would be minus dou u by dou x. So let us put it here. So that is going to give, because this d by dt is there, so x dot will be x double dot plus dou u by dou x is 0, or I can write it to be that mx dot double dot equal to minus dou u by dou x. Now what is the term on the right side in this equation? It is nothing but my conservative force. Okay, can I write it as which is nothing but force? So indirectly this is going to say that any least action with the potential is nothing but F equal to ma. You know very well, right? So there's no confusion. Suppose I consider a least action with no potential. Suppose a particle is on a plane where there is no potential. What happens to that least action? How it will move? So if you do that, let us do that same way. Where the potential is 0, you have only the kinetic energy. So L equal to T, which is given as half mx dot square. So let's put it in that. So this equation will give d by dt of mx dot, because the derivative of Lagrangian with respect to x dot will give mx dot, which is simply 0 because there is no dependent of x component. If this is 0, so my mx dot should be a constant. So let me take it as the constant as something like mv. So m can be cancelled. So I will get x dot equal to v, or if I integrate it, x equal to x naught plus vt, this is simply a straight line that you normally expect. So if I just apply, in a force or the kinetic energy the particle has can move on a straight line when there is no potential in one dimension. It's one dimension problem. Similarly, I can have the least, what would be the least action in a gravitational potential? So I have a particle. So if I leave it, what would be the kinematic equation that can be represented if the particle falls under a gravitational potential? So that's also can be derived beautifully. So you know the gravitational potential explained by mgy, and because the particle is moving just straight down, we have only the kinetic energy term, that is my dot square. So therefore you can take it my dot square minus mgy as your Lagrangian. So now if I take this, apply this condition, so it is going to give my dot d by dt plus mg is 0. So otherwise it is my double dot plus mg is 0. So you can rewrite it y double dot equal to minus g. Now you have to do double integral. So if I do once integral, I'll get y double dot is minus g. If I do once integral, then I'm going to get y dot equal to minus gt plus c, and again I integrate y equal to minus gt square plus ct plus d. I'm going to get it. So otherwise it is going to represent a path of ut plus of at square. That means the least action, when you say, it has to do some motion which is it is as it is. Means if I release a particle under a gravitational field, what is going to say that if I take a particle here and release it under the gravitational field here, can it go like this? Can it oscillate like this? No, it can only do just straight falling with the increasing acceleration until it falls on the ground. So this motion is the least action. That is the only possible process that can happen in that system. That is what we call it as a action that happens to the system if I just leave it on a gravitational field. Now you understand what means least action, right? It cannot take this kind of action, right? Can it be? Or can this particle just, if I leave it here, can I go like this in this process? Unless I am constrained, it is not going to happen in this process. This is questionable, right? This is not called least. This is just falling straight is the least action that it takes in the given condition. So that is what this functional form of the principle of least action, or otherwise variational calculus or calculation of variation, gives an idea about how the stationary path it would exhibit. Okay, but the idea is not to solve the simple kinematics. We are going to look at much more problem. So as we said that the 2 points in a plane, the shortest path is going to be straight line. So that's what we discussed. So let us prove it using variational method. Either is it so? So to do so, let us consider a plane where you have a point A1, A and B with the coordinate x1, y1 and x2, y2. And I can consider any path. I mean, it's not, I don't know how it is going to connect, but I'm just taking any arbitrary path. Now I can define in an elementary length for this, which is ds here, which has a dx component and dy component, and I can write the elementary length nicely, which we already discussed how to write it. So dx square plus dy square under root, and now I can take out the dx outside, therefore it will be 1 plus dy by dx square power root under that. If this is true, that the total path it travels from A to B with this small elementary length is going to be x1 to x2 with 1 plus y prime square of dx. Now, if this is going to take the shortest path between A and B, then it must satisfy the condition that we have explained such that this integral going to be stationary. So if I'm in this case the function y prime x is 1 plus y prime square power half should bound to this condition, that equation that comes out is the stationary, or the path would be the shortest path. So let's see what is going to come out. So since if you carefully look at it, this function do not have y dependent, because if you go back, just you can check it, like there is no y component. Therefore, the partial derivative of this function with respect to y obviously going to be 0. So any no issue with that. So you are only going to take derivative with respect to y prime. So if I take derivative of this function, this is plus power plus half. So it will be eventually minus half. So therefore this term when you do again differentiation, it will be 2y prime. So half gets cancelled. So you will get this functional form of it. And now the d by dx of this function, the partial derivative of f with respect to y prime said to be 0 because this is 0. So if this is 0, I can obviously assume this term is going to be constant. So we can write y prime plus into 1 plus y prime square power minus half is constant. You just square it on both sides to simplify it. So you move it this side. So this y prime square equal to constant multiplied by this function. When you move out, it will be 1 plus y prime square. So you rearrange the term. What you are going to get, that means if I take out y prime square both sides, 1 minus constant is equal to constant. So again I can say y prime square is equal to constant, because anything by any constant form will again give me my some constant. So therefore the y prime square is equal to constant, or dy by dx will be again square root of constant, which is again a constant. And now if I integrate it, you are going to get y equal to mx plus c, where c and m are some constant and the equation provides a straight line. So that means when the function f is applied to the condition of Euler-Lagrange equation, it gives a path or equation of motion which defines what should be the shortest distance between these 2 points. So here we are getting in a plane is just a straight line. I hope now you can prove it very simply without any difficulties. And now let's take a simple complicated problem, that how do we design a roller coaster, right? And we have already seen how the roller coaster looks like, or you have experienced it in a way when you are entering into theme park and enjoyment. Now why we should design it in such a way, the roller coaster should be in a particular shape, and that's also dealing this Barchistochrone problem. So let's take in a plane. So I'm released this roller coaster from here, let's say point 1, and it reaches to point 2. So here the definition is shortest possible time. So now we are going to deal not the path length, rather the time it takes to reach from 1 to 2. And we have already defined how to explain it. The time to travel from 1 to 2 can be written as integral 1 to 2 ds by v. And there is no difficulty for us to understand that one. And ds, we can represent it by any small element that you can express it here. So we can write it the ds element as a dy and dx component. And now since you are at the point 1, which is at a height, so you have a potential energy, and as you come to point 2, you are conserving to the kinetic energy, gives a relation v equal to under root 2gy. So now we can rewrite the elemental length, which is ds here, which is dx square plus dy square under root. Now here I can take out dy outside, such that it will be 1 plus dx by dy square, or I can write dy into 1 plus x prime square, where x prime is dx by dy. Now, it's slightly different from what we did last problem, where we took dx outside such that you got y prime there. Now you are dealing with the x prime. So this all depends on how you are going to solve the problem. Therefore, now because we took out the dy outside, so your function is going to be y, x prime y and xy. In other words, if you relook at our previous problem, we took dx outside so that your function came as y prime x dx integral. Now it is slightly different. So you have to be careful which term that you are taking out of the ds element to make x prime square or y prime square is very important. Otherwise, you will end up in messing up the problem. Now we know what is the functional form of f, and the condition for integral to be extremum is, you know that, now we are going to write it with respect to the d by dy of partial derivative of f with the x prime minus partial derivative with the x is 0. And now you can clearly see here this function do not have any x term. So obviously it is going to give you the partial derivative of f with respect to x. This function is 0. So therefore, now we need to find the partial derivative f with respect to x prime. So obviously there is a x prime here. So when I do that again, it will be x prime by under root 1 plus x prime square. Already you have root tgy, so that is there. And now this term, when you take a derivative with respect to y, you have to find it out. So that is going to be 0 because this term is 0, and otherwise I can say this statement is constant because it's not dependent on y. So we can write it as x prime by this term is turning out to be constant, and I am taking a constant, something very peculiar value, to solve it as 1 by 2a. You may ask, sir, why are you choosing it? This is all taken for simplicity so that you arrive at a complementary solution. So we can square it so that you can remove this all the under root terms. So when you square it, this is x prime square by 1 plus x prime square into y. Again, I take out this constant because it is meaningless. Take out the 2g also. So I rewrite again this constant as 1 by 2a. Now we can rearrange these terms carefully so that, you just expand it, bring out all the x prime square one side, and now we can simplify this term as x prime square, which is equal to 2a minus y by 2a equal to y. So 2a can be cancelled obviously. So it is y by 2a minus y. Or otherwise, we can say that the x prime square is y by 2a minus y. Or we can take it in the under root format. Or we can write it dy by dx. So this is x prime is dx by dy. So dx is here, dy is moved to the right side. Now how would I solve this integral? Because when you do want to find x, you have to find the integral of this function. So to solve this integral very easily, so let us take y as nothing but a into 1 minus cos theta. In that case, my dy would be, this is a constant, this is constant. So this will be varying because theta is there. So a sin theta d theta, because the differentiation of cos theta would be minus sin theta. Already minus is there. So a sin theta d theta. Now we can substitute here. So in place of dy, you substitute a sin theta d theta. In place of y, you substitute a into 1 minus cos theta. So let's substitute it. So you are going to get 1 minus cos theta. So when you put 1 minus cos theta here, so a into 1 minus cos theta, 1a gets cancelled. So you will have 1 plus cos theta coming up. So here you have a sin theta, and the a that commonly here for y would be cancelling it out. Now we can bring the sin theta also into the root. So it will become sin square theta, or I can write it as 1 minus cos square theta. If I bring the sine term into the root, it will become sine square theta, or I can write as a 1 minus cos square theta. So this is again nothing but a square minus b square. So I can write it So we can write it as a plus b into a minus b. So when we do so, then we can write that this way. So a minus b into a plus b. So this is cancelable, and now you have square term. So this can come out beautifully. So you see the function that you cannot solve it. Now by taking some approximation, it nicely come out a integral 1 minus cos theta d theta. So if we do this integration, my x will be a into theta minus sine theta plus some constant. So now what the equation we get for y that you consider in this functional form provides x in this functional form. So x and y you are getting in terms of theta. Now what is this equation giving us? So this equation indirectly gives the path of variation as this one. So if you do x square plus y square, then you end up in similar way. So this is the path, is a part of cycloid that we have shown earlier in initial discussion. So you take a circle and keep a point and move that on the straight line to provide a path which would give the cycloid motion. That is the equation which certifying this cycloid motion. And now you can see this path is the one that we have also schematically shown. So you have three different paths. If you release the particles from all three, you see which one reaches faster. The red one reaches faster, and that is how this, your roller coaster designed in this shape, so that when you release this roller coaster from here, it reaches to this point in a shortest time to give you maximum excitement. And that's why roller coaster is always you experience a lot in feelings. That's because you are changing things in a shortest time, and this is the functional path which would give you the shortest time. Not even a straight line, it has to be some curve, and that curve is a cycloid. Yeah, it's obviously you cannot believe it, right? When you move your roller coaster here, you have to apply energy, so that when it comes here only, you are going to release it freely, and that movement here, it will be so fast. To reach the shortest time to come, will have to follow this functional form of it. I'm sure now you have a positive feeling on the roller coaster, right? If that's understood nicely, let us take a problem to take away home. Sorry. The shortest path between 2 points on the surface of the sphere that we have discussed, also we are going to solve it. So what we have, let's assume the sphere like this. Okay. Now to solve this sphere, this is in a line, so I just will make it little blurred by applying a white background. Now it just dulled it. So and then you can project it so that it looks like a circle on a plane. Now let me consider a point P1 and the point P2. Now how these 2 points will be connected between these 2 points, right? How it will be connected, and then does it has to follow certain condition? That is, will this connecting path follows a complete cycle on a sphere in this particular form, or in a different form, or this form? One of these will it form? That means when I connect the point on a surface of the sphere, will it take some form along the given path? And that is what we have to determine it. And when you want to solve the problem in sphere, you have to take the spherical polar coordinates, and the element, the dr vector for the spherical polar coordinates given as dr r cap, radial component, and the theta component r d theta theta cap, and the phi component r sin theta phi cap. This you have already done nicely in the lecture 3 and 4. And now if I assume that it is moving on it, then we need to find the elemental length ds, which is nothing but dr square. So which will be dr square r square d theta square and r square sin square theta d phi square. Now we need to take, now since we are only moving on the surface of the sphere, my radius will be always fixed. Whether I move in a point 1, point 2, it is always connected to the radius only. Therefore, r is always fixed to be constant. In that case, since r is constant, my r dot would be 0. So therefore, the dr square can be off. So your elemental length ds square is a component of r square d theta square and r square sin square theta d phi square. Now you take this and put it in that function that you know f of y prime x. Here it is theta or phi, you have both to play with. So in this case, you can either take theta prime phi, or you can take f phi phi prime and theta in any functional form similar to what we did it in y prime x, and then you can solve the integration and find out what would be the solution for it. Try it. But otherwise, we can solve this problem on Saturday class to understand what the functional form it would give. So keeping that, now let us rewind that we have started with the integral part having a function f y prime x dx, for which if you want to state that integral path to be stationary, then the condition that has to be imposed is nothing but Euler-Lagrange equation. And then we have, using this Euler-Lagrange equation, we understood how these kinematic actions that turn out. And then we solve the problem, the shortest distance between a points in a plane and shortest time in the case of between 2 points in the case of roller coaster. So the action integral that goes for the time part between time t1 and t2 can be in this functional form, gives the idea of the least action. We call it as a principle of least action, that any path of a particle or of particles in a given configuration space is the one that yields the value of the action. For example, that we consider when you leave a particle on a gravitational field, it just goes straight down with the form of y equal to ut plus half at square. It cannot have any other form of it unless you impose constraint on that motion. So this kind of action is called Hamilton's principle of least action. We will discuss more about this Hamilton's principle of least action in the next 2 lectures. That's what we are going to change from Lagrangian to Hamiltonian, and it has one benefit and it has one consequences. We will discuss about both of them with respect to Lagrangian and see which is simplest. So with that, we will stop here.